Okay, continuing on with 16.5, we left off after example 1. This theorem 3 that we see here very nicely says that if f is a function of three variables, if we took the gradient of that function, and then if we took the curl of the gradient, we'd always get 0. We can certainly prove that. The author proves it relatively quickly in the book. But I'm not going to do that for the sake of time right now. Take it on good faith it's true. You can read this on your own. It's a quick proof with Fubini's theorem. But recall that if the gradient is equal to a vector field, or I should have said if the vector field may be expressed as the gradient of another function, which we'd call little f, or the potential function, then capital F, this vector field, is a conservative vector field, we would say. So this is going to follow immediately that if we look at this next little statement, if f is conservative, that is, if capital F is really the gradient of some potential function, then the curl of f, that is the curl of the gradient function, must equal 0. Well, that's just restating this theorem that we just mentioned. However, I want to make mention that the contrapositive is also going to be true. If I were to negate the conclusion, if the curl of a vector field is not 0, then that vector field is not conservative. And that can be very helpful. Take a look at example 2. Show that this vector field that we had in example 1 is not conservative. Well, from example 1, we know that the curl of vector field f was negative 2y minus xy I plus x times vector j plus yz times vector k. And that means that that curl is not always 0. Certainly it could equal 0 with the appropriate choice of x, y, and z, but in general there are many values of x, y, and z where that would not be the 0 vector. What does that mean? Therefore, f is not conservative. So if your curl is not 0, your vector field is not conservative. By way of comparison, we can immediately take a look at this next theorem, number 4, which is wonderful, because now this says if your vector field has continuous partial derivatives, if the curl of that vector field is 0, then f is a conservative vector field. So a wonderful fact is, when we take the curl of a vector field, if it's not 0, what we just saw a moment ago, if the curl of a vector field is not 0, that means the vector field is not conservative. This statement right here from theorem number 4 says if the curl of the vector field is 0, then it is conservative. So practically speaking, we can take a look at example 3 and many other problems like this, and just take a look at the curl of that vector field to determine whether it's conservative or not. That's what we're going to do very quickly right now. We're going to look at the curl of vector field f. And I do want to say, again, it's unfortunate that our TI-89s are not going to have a curl built into it. That tool, sadly, has not been entered in. We have to evaluate curls by hand. But notice what's happening. It's a 3 by 3 determinant. We can look at this in terms of columns. Look, we have an I column. We'll have the del operator as a derivative with respect to x. Put in your I component, y squared z cubed. Your j component of your vector field is 2 xy z to the third. And then finally our k component is 3xy squared z squared. And to work this curl out more quickly, I'd like to make mention that you don't always have to write everything out exhaustively. You can do this a lot more quickly in the following way. Cross out your I, JK row and your column of I. You will now have a 2 by 2 determinant remaining, and here is one of the diagonals. And in fact, what we're going to do very quickly, without even needing to write this out, just look at this diagonal that I highlighted. Take the derivative with respect to y of 3xy squared z squared. Well, we'd get 6xy z squared. Then I'd say minus. Well, what now? Well, we would take this other diagonal, which will be a derivative with respect to z. Remember, down here we have a z cubed, so bring down the 3, we'd get 6xy z squared, and that will be what's in front of your I. Now, by the way, you can see this is going to wipe out to a 0. When we work out our k component, I'm going to erase some of this in the meantime, please remember that we always subtract. We'll write a minus as we're writing our j component. I should have said our next component, our j component. Again, keep that top row canceled out, but drop down that j column and put a minus sign out in front here. Do the same thing. We're going to look at our first diagonal, which is coming this way, a derivative with respect to x of 3xy squared z squared. We'll drop that x out and we'll have 3y squared z squared minus, well, now let's look at our other diagonal. We can look right here, a derivative with respect to z of y squared z to the third. Drop down the 3 from the z, 3y squared z squared, and then of course this is our j component. Well, you know, we can continue on this way. We just have one more component to work out, and that's with our j, our k, I am so sorry. And look what's about to happen. We will now cancel out this k column. And what is remaining? Well, we go back to a plus, and this time we can draw in our diagonals again. We can have derivative with respect to x. Well, that's going to be 2yz cubed minus, what's our other diagonal? Well, look right here, a derivative with respect to y. It was y squared z cubed. That's going to be a 2yz to the third. 2yz to the third. If you look very closely, you're going to see that each of these coefficients of the vectors are going to wipe out to 0. This becomes 0i plus 0j plus 0k, which effectively is just 0 itself. That would mean that my curl of f is the 0 vector. It means I have a conservative vector field. So we've been talking about the curl quite a bit. The reason that we use the name curl is that it's a vector associated with rotations. A particle near a given point, x, y, z, in a fluid might tend to rotate about the axis that points in the direction of the curl of f evaluated at that point. So that's why it's got that name. Now, there is a second type of operation on vector fields. This, by the way, is a much easier one because it's not even a vector at all. Let's say we have a vector field f, pi plus qj plus rk, and the partial derivatives exist. The divergence, we had the curl of a vector field. Well, right now we've got the divergence of a vector field. Very plain and simply, notice in this box there are no I, j, k components. This is not a vector at all. It's very simply the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. And to write it another way in terms of del, of course del is not going to be involved with a cross product now, but rather with a dot product. I'll be honest with you, I think the easier approach to determining a divergence is to use the first definition rather than a dot product. Plain and simple, what this would look like, for example 4, is this. We could take our partial derivative of xz with respect to x plus our partial derivative of xyz with respect to y plus our partial derivative of negative y squared with respect to z. Well, our first derivative, you would just get a z. Second derivative here in the middle with respect to y, I think you could see you'd have xz. And our last derivative, working this out with respect to z itself, is 0. Notice that there are no vector components. This is just z plus xz, and that's really what we have as our final answer. Here's another theorem. Theorem 11 says if you have a vector field and p, q, and r have continuous second-order partial derivatives, then the divergence of the curl of that vector, when you use these two operations in succession, would be 0. Now again, I'm not going to prove this for the sake of time. It can be proved relatively quickly with Fubini's theorem, and it's not a super difficult proof, but the divergence of that curl would be 0. Let's real quickly take a look at example number 5. Example number 5 says, show that the vector field xz plus xyz j minus y squared k, which, by the way, if you just look at that, we just did that problem, that vector field cannot be written as the curl of another vector field. That is, vector field f really could never be the curl of some other vector field g. Well, they're saying, show that that's the case. Well, this is called a proof by contradiction. Let's assume the opposite just for a moment, and we did this even in AGT, accelerated geotrig. We could assume for a moment that it was true. Let's just say that vector field f is the curl of some other vector field g. Well, we can say from example 4 above, the divergence of vector field f was equal to z plus xz, which clearly is not always going to equal 0. Here's the thing. If this statement was true, if where we have vector field f, it's really the curl of g, then we'd say then, according to what you've just written, hey, just replace vector field f with the curl of vector field g. Then the divergence of this curl would be z plus xz, which again is not equal to 0. But this is a contradiction. So what does that mean? It means that our assumption would be an error. Why is it a contradiction? Because we know that when we take the divergence of the curl of a vector field, you will always get 0. So therefore, this vector field cannot be the curl of some other vector field. All right, well, we're going to wrap up just briefly talking about this other material in a tiny epilogue.